Okay, you ready? Ladies and gentlemen, welcome to another wonderful episode of the New York City Category Theory seminar. Today we have Sophie de Espalunga. You're going to have to say that yourself. And she's talking about building all of mathematics without axioms, an n-Categorical manifesto. Sophie, take it away.
Hi, yeah, thank you very much. I am very happy to present this work. Um, so, according to the tradition, maybe I should present myself. So, I was born in Lyon, which is a city in France, and I made my undergrad studies in Paris, my PhD in Lille, under the supervision of Benoît Fraisse in algebraic topology, and now I live in Paris. Okay, is that good?
Perfect.
Nice.
Okay,
Okay,
perfect.
so I just began to become interested in the foundations of mathematics during my PhD thesis, um, because I needed to manage large categories in my constructions, mostly in a two-categorical framework, and to describe. I needed a higher level of abstraction to describe certain structures arising in my study of iterated loop spaces. So um, the the idea of building mathematics without axioms is to define everything because generally axioms um, are kind of a way to define the undefined terms. So in this talk and everything will be considered from an internal point of view, and there is no external word in which we can evaluate the and understand the objects. So, okay. Another important point is that all of the dependencies are encapsulated by functoriality. So there is no undefined stuffs, and everything that depends on something is made precise through functoriality. Okay, I will first present, before I present the definition of an n category and how we can do math within this framework, I will um, recall some basic elements of mathematical language, the way it is done, the way mathematical language is formalized, and why it could be better. Okay. Okay, so a brief the the notion of an axiom and of truth evolved a lot through history. Um, Before the formalization of mathematical language, mathematics were written in natural language, and axioms were considered as proof irrelevant truth. So the father of logic is maybe without doubt Aristotle, that he introduced the concept of syllogism and hypothetical deductive reasoning. So Euclid later applied this process to mathematics, and he he formalized geometry in an axiomatic way. And then, well, basically, um, nothing happened until Leibniz, um, which first had an idea of proving the axiom. He thought that all of mathematical language could be reduced to definitions with an only axiom given by the indeterminability of identicals. Okay, so since Leibniz, there were a big process of formalization of mathematical language with Boole, Cantor, Peano, and Hilbert, and the boundary between an axiom and a definition fades away. So axioms were now acquire a definitory meaning, and we are then able to construct some models that satisfy the axiom. So the syntax and the semantics split at this time. Then, okay, and this culminated in Hilbert's formal systems that eventually gives rise to mathematical logic. So well, um, with the rise of formal systems was also the beginning of the problems. We had Russell's paradox, like Gödel's incompleteness, set theory, Tarski's indefinability of truth, okay? And the notion of truth then acquired two distinct meanings as one internal and the other external, undefined, that we don't really understand. Okay, and then we have category theory. But um, the problem is that in the definition of a category, we have this somewhat mysterious collection of objects, which is not really satisfying, I think so. Okay. So the idea of formal systems is to enable to deduce truth about some things from very simple truths about those things. So if you formally assume that some statements hold, which we call axioms, and some statements can be deduced from others, which are rules, then you can combine all of them and obtain all the syntactic consequences or logical consequences. So we obtained a notion of derivability and entailment, so which we write as a like that, which means that J can be derived from K within the system by using proof tree. So proof tree is just a way to generate all the logical implications given hypotheses and conclusions. Okay, so this is quite prac practical because the results are then valid for any object that satisfies the axioms. So to reason about formal systems, there is well, a grading of meta levels. So at zeroth level, we have some things which are undefined stuffs and that gain a meaning. So, and then we have the judgments. The judgments are statements about the things, and the thing we care about is whether it is derivable or not. So we have a truth value associated to this judgment, which is J, which corresponds to the fact that J can be derived within a system. Okay. So the rules are interpreted as a way to derive the conclusion if we can derive both of the premises. But so this is what we expect from such rule, but we'll see that it is more complicated. And the axioms are just some things that are supposed to be true. So now, if I have a model in which the axioms and the rule hold, we can deduce that the entailment is valid as well.
Well, what's the difference between an axiom and a judgment?
Um, an axiom is a judgment that is supposed true.
Oh, okay. Okay.
Okay, and so we have this notion of entailment, which is quite um, a meta at a meta level higher because we reason about the judgments of the formal systems. And what we expect from this entailment is that I can effectively deduce J if I can deduce K, but then problems arrive. So yeah, ultimately we only care about the derivability of judgments. This is a notion of truth that is considered in formal systems. So formal posets whose objects are the concatenations of judgments and whose order is generated by the rule in a way that is compatible with concatenation. Usually, we are not allowed to have a conjunction of judgment as a conclusion. So you can just add manually and obtain some stuff like that. Okay. So um, each time that you have a rule, it gives a relation between the concatenations of the premises and the conclusion. And this need to be compatible with the product so that you also have this. Okay. Well, so as I said, our interpretation of a deductive system is as follows. We have a judgment and we ask whether it is deducible or not from the rules. And each time we have an entailment, then we know that whenever the premise holds, the conclusion holds as well. And this morphism is constructed by using this can be visualized as follows. The empty judgment considers to okay, so the empty judgment is derivable because the morphism is just constructed as such, and it is part of the structure of a formal system. It's the judgment that gives the axioms, that encodes the notion of axiom. And the derivability of a product of judgment is the product of the derivability of each judgment, so that the concatenation effectively encodes the fact that we want to have both of them. Okay, and now we are good because each rule yields an implication between the products of the premises to the conclusion.
Excuse me. One thing I did not quite understand the role of axioms because something can be derivable without axioms, right? With the empty set of axioms.
Yeah,
So
they have no particular role. I just wanted to emphasize the fact that the empty judgment is structurally true.
yeah, but axiom is something is supposed to be on the left of Tornestyle, right? Or somehow what is derivable you also call axiom.
No, I think certain things can be derived even if they're from not true things. In other words, you can assume the moon is made out of green cheese, and you can assume this, and you can get conclusions based on that, but it doesn't mean it's true. But there has to be some type of there's a word missing here, namely what things can only be derived from axioms.
Right, right. No, but certain things can be derived from nothing, right? So they are just derivable formula. You are not supposed necessarily to have something on the left. You may simply derive it just from your rule by introduction rules, right?
I don't know.
From a from
Let's
empty
so
set of axioms. I think.
let Sophie answer.
Mhm.
Uh, I'm not sure I see the point. It's just that what I say is that the entailment, the deducibility of a judgment corresponds to the order relation given by entailment with the empty judgment on the left, which is the definition, right? But if J is a rule, it can I you can derive some rules, but you also can derive some judgments. It depends on the formal system, but in the simple one, with no internal entailment or something like that, every truth comes from axioms. But
Mhm.
it doesn't matter because the the axioms and the rules have the same meaning in the end.
So that's the word I was missing too. Truths are things that are derived from axioms, but other things can be derived from Many things can be derived from empty sets or other judgments, but they're not necessarily true.
No, they are just derivable. Yeah.
Right. Okay. Andre, you
But
happy?
uh, uh, yeah, but just those things which you may derive from empty, just from nothing, like you say, introduce. Say you may have some introduction rule, right, with the empty set of premises, if I understand correct, right? Or so you may just introduce certain, I don't know, constant just without any action. So how you would call this? And you would say this thing would hold, right? I don't know. In that question, would you call it true or not?
Um, Maybe it's confusing because the
Mhm.
empty set. I'm not talking about something that is initial, right? It is just the empty judgment. I needed to find a name because
Mhm.
uh, it's usually unwritten. Like you see, axioms are represented as just a vertical bar and then the judgment, but nothing up. And here the empty is just no no premise, which is interpreted as true. And
Yes. Yeah. So you would call it true, even if it's no premise, right?
yes, yes,
Okay.
yes,
So you have like two cases of truth, one which comes from axioms and another, the other that comes as we
yes.
just described.
This is
Okay.
a structural truth. This is
Yes.
truth internal to the judgment, and it's part of the structure.
Mhm.
Okay, I hope it's clear. Maybe it, it will
Can
become
can you just turn to the first slide, please? Because I think you had empty set on the left of the turnstile. Somewhere I saw it, I think. So, uh,
uh, yes. Um, the empty set on the left at the turnstile is exactly it can be removed.
okay,
Uh, this is just the empty judgment, but I couldn't just write nothing. I needed to name it.
okay,
Okay,
okay. Thank you.
so for instance, the turnstile J means empty set turnstile J.
I
And
understand. Okay. Hmm.
okay, thank you. So this is the way I construct the morphism.
Hmm.
Okay, so but there is a significant problem with this deducibility notion because the deductive process is actually confined to Boolean logic, but it fails to benefit from its feature. So while you have a structural true, you don't have a structural false. And in the real life, you have the notion of contradiction. You cannot derive a judgment and not derive it at the same time. So there is this notion of false, which from which we can derive everything, and that is not structurally integrated to formal system. So, so for instance, you can have a judgment that is whose deducibility yields a contradiction, but it it won't give the fact that this judgment entails all of the other judgments for all judgments. And there is another problem. It's that in in real life we have a proof-based implication. So to show that 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 a judgment that the derivability of a judgment um, yields the derivability of another judgment, we suppose that the first one is derivable, and we constructed a proof to derive the second one. But inside the deductive system, you cannot derive an entailment between two judgments from the from an external implication. And this makes some truths very hard to deduce in a formal system, and because some of them are sent outside, and this gives rise to admissible rules, which are true but not derivable, because and true in the sense that they don't change the theorems of the deductive system, and but um, but they cannot be derived from the existing rules in the system. So you have this morphism, um, which is not um, which is not
Oh.
not subjective, full. So you may have an external implication between judgments of a formal system, and this implication will not be valid internally.
I'm sorry, aren't there deductive systems where the last thing is done? Where Beweis, how does it go? That if Beweis of J implies Beweis in K, that means Beweis J are okay, or something like that. I
What
mean,
does it mean?
the the last the last proof-based implication that you
Yes.
can't right that.
This means that to prove an implication, a logical implication, we we just consider.
I agree. I understand that in the real life, but aren't there deductive systems where such things do happen on the left?
I think it's it requires the deductive system to be structurally complete. I'm not sure, but I think so. And
Okay, so
then
it's
yeah,
in
this is
certain times it
a
is. Okay.
definition of structural completeness, because and there I'm not talking about any notion of internal entailment. I'm just I'm talking about exclusively the iterations of this vertical bar. So um, if the deductive systems enables to derive some rules from this implication, then this morphism is an equivalence, and the system is structurally complete. And then you may have some problems with Gödel's theorem, because the fact that the system is structurally complete imposes a lot of stuffs on the system. So it's okay. Um, well, so now I'm going to try to convince you that internal reasoning works better. Well, so we have this Cartesian poset with an entailment relation that gives the truth value and that sends those truths outside of the system. But consider an Nating algebra object, you have only an internal stuff, and that's why this is precisely what other notions of entailment try to do, in my opinion. So you have this concept of derivability, which is a truth value, and in the framework of an Nating algebra, it is just the same judgment, because we definitely want true to be the terminal object, and so it's act like that. So the derivability is the identity. Okay. In a deductive system, you have the empty judgment, which is a structural truth, and which we also have in a Nating algebra object. And false can be introduced, notably by using internal internal morphisms that I added to the deductive system. And but it is not a structural false, and its relations with the external negations are not clear. So I think that there should be a structural negation included to deductive system that acts functorially in the sense that it defines a contravariant morphism which enables to deduce the opposite of a judgment um, from an entailment, the opposite thing. Okay. And
So, just a question to be sure I understand this difference, internal, external. Uh, Say the case of sequent calculus, would you call it external or internal? Because we do have there as a calculus, right? The derivations which go from uh, probability of one thing to the probability of something else.
yeah, the problem I think is that
Mhm.
well, we can always like manually add other notions to have internal reasoning that works, but the interaction between the internal and the external are always we always lose something when when um, when we add the stuffs, and I think it's quite remarkable with regard to admissible rules because you can change the system to have all the admissible rules that derivable, but then you will change the internal home. It's it changing it changes whenever. Well, there is always something that will you will pay this somewhere. Um, okay. Yes. Okay, let's move on. Okay, so you can consider the derivability of a judgment, and whenever it is defined, the derivability of its opposite. So in a deductive system, this is a truth value that expresses its consistence. Well, it could be simpler and be just structurally false, as it is the case by modus ponens, just simply in a Nightingale algebra object. Okay, so you have this I talk about. So you have those derivable rules and admissible rules which define two distinct truth values, and that adds a lot of complexity within the system, which is not the case when you reason internally. So, okay, let me just say that you can't have a fixed point for internal negation, and hence I think that all of the definability of Gödel stuff should be rethink with regard to the contravariance of the negation. So just to make it concise, there are some structural shortcomings in the structure of a deductive system, namely that there is no built-in acting algebra structure. So we can always add some stuffs, but then we obtain a proliferation of implication symbols that does not have the same meaning, and we eventually manage to make them equivalent, and so we add just more and more rules, and this leads to a very tedious formalizations of the rules of a deductive system. And another important fact is that the reasoning that is allowed in formal system is very specific, and it is exclusively deductive. You you can't use hypothetical deductive reasoning because you can use hypothetical reasoning. Well, which is not the case when you have an internal entailment, but this is not part of the structure of deductive systems. Okay, and so you have those rules that are valid externally, but not internally. And finally, the expressiveness of deductive system reduces to Boolean logic, maybe without the if, So we have the then and the end. Um, fine. And you cannot express like all the truth values of derivability. So for instance, I know that most of the many problems arise when working in deductive systems for some things like modal logic or more general logic, because we restrict the derivability to true or false. But I think that we should be able to express the fact that a rule may be derivable, or the truth value of a rule is different from just true or false. So the purpose of formalization of mathematical language is to assign a meaning to combination of symbols. So the notion of a truth value is actually very connected to that of a statement. And okay, so say that an expression is a combination of symbols, and a statement is an expression assigned with a meaning. So a meaning can be defined as a meaningful combination of meaningful expressions. And by meaningful, I will say that I will define meaningful as something assigned with the truth value. So the truth value are the possible values for the evaluations of statements, and they form the basic block of uh, the constructions of meaning. So to assign a meaning to some expression, we define it. So we assign a meaning to an expression by forming a meaningful combination of meaningful expressions. And the ultimate objective is to determine the truth value of the statements. So the evaluation process stops at truth value. And the value of a truth value is just itself. So in this talk, the statements are evaluated as either false or true, which I will define in a minute. But we have to keep in mind that this is much more general. But I want to talk about n categories, and they are actually quite like generated directly from Boolean logic. So this is the reason why I'm using those truth values. So let's go back to the old truth tables. So, okay, I want to define an implication between those symbols, which I decreed have a meaning. And the only important thing is that on the diagonal, it should be true. And I also want true to be the terminal object. And this is quite convenient to obtain the notion of a negation that acts by contravariance. So okay, the Cartesian product and implication are just defined as usual. And each time I have a poset or something like that, I may write either with okay. I also write the implication as b of x, y. And okay, so we can define now the equivalence of truth values as the conjunction of the implication and its reverse implication. So with this formalism, we can uh, derive this expression, and in the sense, so this is true for all of the values of x, y1 and y2, in the sense that it evaluates to true. Just have to look at the truth table. So the idea is that um, I'm going to introduce another way to talk about truth value by introducing the notion of proof, which are just elements of the poset of which are analogous to elements. So truth values are identified by their proof, and true have a proof, false has no proof, and if I wanted to have a maybe truth value, well, maybe may have a proof. So this means that true has proof is true, and false has proof is false. To formalize that, we just assign the symbols as follows. So, okay, for any variable symbol, I will talk about that in a minute. Gamma, I say that gamma is an element of type true, is true, and beta is of type false, is false. With this simple equation, we can do a lot of things. And okay, consequently, if I define a statement to be true if it has a proof, well, the provability of the statements becomes equivalent to the truth of the statement, which is just this statement. The implication is determined by its behavior and proof, and I will show how to write it formally in a minute. And the proof consists, consider a proof of a product. It's just the data of a proof of each of the factors. So, okay, so P is true by definition if and only if it has proof. And this is also equivalent to P, which is just an implication from true to P. And an element of the implication, a proof of the implication consists in assigning a proof of Q for each proof of P. And
I'm confused by this. Is your system not allowing for the possibility that there are truths that are not provable in the system?
Truth is defined as provability.
Yeah, but look, I mean, this is I mean, I can imagine at least, for example, a statement that is true for every integer, but there is no uniform proof. So I don't have a proof in the system for it.
Oh, I'm not saying that I am able to construct a process that gives this thing. Actually, everything. It's not a process something. I don't say that true means provable in the sense that I can write the proof. I just say that
Yes, that there exists such a proof. Yeah, that's a statement. I understand what you're saying, but why can't I imagine, for example, a proposition which is true for every integer, but for which there is no proof in the system that that's the case? Is it impossible to imagine that, or
um, yeah, I think so. I don't know, but everything works internally, so um,
okay? I just meant to try to
is
get
it true
clarification.
if it is well
May I
maybe
just a short comment on? I think here we really have different, how to say, terminologies, right? Of course, with kind of different background ideas and philosophies about true, but which are well known, right? So what you're presenting is a kind of constructive theory of truth as existence of a proof, right? And then, of course, all these results like Gödel, etc., they would need to be, how say, reformulated. I mean, not mathematically, but in a, how say, natural language. So it's a different kind. So I think yes, here we simply cannot talk about something which is true without having
Okay,
an evidence. And
okay,
that's just different conception of truth.
okay, okay. All right, thank you.
yeah, thanks. Um, okay, so Okay. The main idea is to the object that I will talk about here will be equipped with a predicate that gives conditions to okay, the objects are equipped with what I call a predicate, and that maps a variable to a truth value, which we regard as x is an element of type x. So this is the zeroth level, and by variable, I mean a symbol of the language that has not been assigned a meaning yet. So the the we have an object which corresponds to the maps from the variables to truth values, and it is itself equipped with a predicate that gives some conditions for P to be such a predicate. So it consists in associating a truth value P of x to each variable x, and such that if x and y are equal variables, then the truth value P of x should be the same than that P of y. So this encodes substitutions of variable, and this also ensures that you do not have some hidden dependencies in the truth value given by P of x. So now if I look at what it means for this thing to be an element, such a predicate, I obtain that I can substitute and obtain that such predicate corresponds to the data of a truth value depending on the variable x for each x, and such that it is compatible with equality of variables. So this predicate should be seen as a type constructor and gives a way to define the elements of x. So we will say that an element of x is a variable symbol which is equipped with a proof of the proposition that x is an element of type x, and that corresponds to assigning this variable with a meaning. Now, the definition that generates all of the hierarchy of n categories is as follows. So I define, I say that X is an n category if it is equipped with objects, which is the upper line, and morphisms. So I just talked about the truth value. So an n category should has a way to construct some objects. It should be equipped with a type constructor, a process that from which we can construct some elements of this category, n category. And the morphisms consist in the data of an n-1 category for each elements of x, together with an additional structure that promote this mapping to an n functor. So for the moment, this does not have a meaning, and we are going to see how to provide this sentence with meaning. So first observation, x is a variable here, and n is variable as well. So you can replace this by anything. It's just I write n, but it could be any other symbol. But for evident reasons, I'm writing this symbol by n. So to assign the right hand side with a meaning, we will assign each of the lines with a truth value. And the result is obtained as a conjunction. And as I said, the data of a proof of a conjunction of the truth values is given by a proof of each of them, because it's the syntactic consequence of the definitions of truth values. So the first step is to, okay, here. Okay. The point is that this is going to this is an object which is equipped with a predicate that I defined earlier, and cat okay given that each of the objects that I defined are themselves equipped with a predicate, if whenever this symbols acquires a meaning, it has a predicate, and I can apply it to something and I obtain a truth value. So I need to manage to give this a meaning while X is not defined as an n category yet. So for this purpose, I need to prove that cat n-1 is an element of type cat n, and I need to define an oppositization and a Cartesian product, and then an n category of n functor between n categories, but which should be inductive, because here I just know that there is a predicate of objects, but I don't have the morphisms yet. So giving this a meaning will be done in a minute. So the opposite of an n category, suppose it is an n category, can be defined as follows. So I just substitute x by x up in cat n to see how to what should I prove. So I just say that the objects are given by the objects. The object of the opposites are the same as the objects of any of x, and whenever I have two elements in x up, which means that x and y are in x, then I define x up of xy as the switch x of y x y x. Okay, which is an element of type cat n-1 provided that x is. So I obtain we can obtain an isomorphism between the opposite and the opposite and the initial object inductively as well. So first we can note that pointwise it holds, and then you just you obtain a structural morphism for the opposite that establish this. So this is usual oppositization. And we can make this oppositization functorial by using higher oppositization functors, because the opposition at level 1 actually acts at a higher level of opposite in the category in which it lives. So the Earth opposite of an object is defined inductively as the object that has the same object and whose morphisms are just satisfy this. The products are inductively defined as well, and everything that will be defined in this talk works by induction. So this is a very convenient way of defining things in a higher categorical framework. Okay, so to give an element of the product consists of providing an element of each of the factors, and then the morphisms of the product are defined as the n category obtained by the by product of the morphisms. So you just have a better expression diagrammatic here. And by construction, this product is equipped with projection morphisms that eventually render it universal among such morphism. And so the product is the right adjoint of the diagonal.
Sorry, just stupid question. So do I understand correctly that to define a product, you use opposite category?
Yeah,
Yeah,
yeah, I need it because
yeah.
to define any object of cat n, I need to define its structural map, and the structural map has for its domain
Mm.
the opposite of the opposite times the object. It's
So you want this counter variant functor, right?
um,
No.
well, it is contravariant because in the
Yeah.
first it's always contravariant. It encodes the contravariance will encode the fact that it's a pre-composition or post-composition.
Okay. Okay, thank you.
Okay, so uh, we can initialize this definition with the first levels and write B for cat 0 minus 1. So we call that for any truth value, I had a truth value of implications which for which the true is terminal. So it will actually give an empty condition. So again, if I substitute n by minus 1 in the definition of being an n category, I obtain this thing. So this is just the same definition, but B has been replaced by cat 0 minus 1 has been replaced by B. And I think maybe I had an arrow and I write it in this form because it's more obvious that this becomes a true condition. So actually, the data of a truth value here then corresponds to the data of its proof and an element of type true, but being an element of type true consists of nothing because it's always true. So we obtain that the truth value is equivalent to the data of its predicate of proof. And not only this equation highlights the proof determined nature of truth value, but it also shows that B fits into the system, and so that we can build n categories from this. Now, to prove that B is an element of type cat 0, we have to show that it has a predicate that gives its elements, which is just true because of what is written here, and that the implications determines morphisms in cat 0, but we have not defined the notion of morphisms yet. So, but it will become quite evident from the definition. Okay. So to define the n category between the n category of n functors between n categories, we need to show first and hence define the elements of this n category, and then the natural transformation, which just corresponds to the structural map of this n category. Okay, so the first step is to give the conditions under which something can be defined as can be endowed the structure of an n functor between n categories. So the data of an n functor between x and y, by definition, is the data of an object of y for each object of x, and together with an object of a coend, sorry. I think the notation is reversed, but it's an and. So something like that. So this has no meaning for the moment. The end is defined by a universal property. It encodes naturality, and it enables to construct things by induction. So it can be hard to make explicit, and I do not have the the I don't have a precise inductive formula to define those the elements of this coend of this end, but because it actually involves lots of iteration of ends, and it becomes quite complicated. But
and what the integral stands for, how you
well,
use it.
It is the left adjoint, no, it's the right adjoint of the home functor, and but something important to from directly from the definition, you can deduce those equations. The data of an element of the end is equivalent to the data of a natural transformation from the home map, the structural map of this to this. It's the usual definition of an end, but generalized to the level n. So it's just the adjoint of the morphism. So something nice with this definition, it actually yeah it resembles a lot path induction in homotopy type theory, because yeah it follows the same principle. So now if I want to construct an element of this end, I need to yeah, because I want the unit lemma to hold as well. I okay, I have those equations that gives a higher morphisms, but okay. Okay, so suppose I have for x and y of type x an n-1 functor from the set of map the n-1 category of maps in x to the n-1 category of maps in y. Then I say that this is natural, or equivalently that it induces a map into the end. If I have a morphisms at the higher level, which act on the product of the opposite, an iterated product of opposite of x, and that enable to manage the relations between f on the map and the composition in X and Y. So the degree decreases at each step. Here you see this is an object of type cat n minus 1, and hence maybe okay. So this is in cat n minus 1, and therefore you have an n minus 2 category of maps given any objects within this thing. So okay, so the degree as decreases, and F2 expresses a compatibility relation between F and F, and you can build the elements inductively by using this principle. Okay, so okay, so here we just gave the object of this n category. So now we have to provide this n category of functor with morphisms so that it actually becomes an n category. So the second step is to define an n minus 1 category of well, what is usually called natural transformations. And for this purpose, we just set that the natural map between functors are also given by this coend. And this is given that this one is an element of type cat n minus 1, because y is in cat n. I have an n minus 1 category as required, and we have to show that this assignment is natural. So for this purpose, we have to build the composition, which is just a straightforward consequence of the structure of Y, which is not the case for this is not straightforward at all, and it is kind of abstract because it is defined as an adjoint, but this one is actually straightforward.
Sophie, just a short question. One thing I don't quite understand, why it's the same n. So x and y, they're like n categories, right? And these functor categories also with the same n. But if you take, I don't know, say just sets, functors, and the natural transformation that rises, right, that would give you two categories. So one would probably expect that if you do this, you would get n plus 1 here, not?
Sorry, if
No,
any
no, 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 no. The idea you have a say some categories, right? And you make a category of functors and natural transformation, and so kind of naturally you rise your n. Say if you start just with a plate categories, then functors, natural transformation, that would give you two category of first categories objects, functors, and natural transformations, right?
yes, but
So
mhm.
so why it's the same n on the left and the right somehow?
Um, okay, I'm not sure I get it. Just are you talking about this n and what is
No, no, just on the top of your page, right? So x and y are n categories, right?
uh, um
But
X and y give
she shows n minus 1 to n. at the right end of the line you're talking about, she has an n minus 1 there.
Yeah, but that's induction. But what I'm talking about here, we have X and Y and categories, right? And then you have these functor categories or functors from X and Y and with natural transformation. And that's again N categories. And I just wonder, would that be N plus 1? No, maybe I'm mistaken. Because some...
No, but this one is an n minus 1 category here. Just consider the two category of categories. We have a category of functors and then a set of natural transformation.
Okay. Yeah. Okay. Thank you. I'll think.
Okay. 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 So now n functors have been endowed the structure of an n category because we have those objects which are functors and those natural map which gives the structural map of this object and achieves the definition. Okay, so there is just a last step to show that cat n is to prove that cat n is an n plus 1 category. So again, if I substitute the definition of being an n plus 1 category this time by cat n, I obtain the following. So the objects are just the definitions that I gave earlier, and then I need to show that n functors defined a map like that to have the structural map that defines n plus 1 categories. So we need to promote this mapping to an n plus 1 functor. Okay, so it is quite visual. I'm sorry because it's not very beautiful, but so given to show that this is natural, we have to define an n functor that will give a post-composition and pre-composition. So this is so and it acts like this. So this is a reason why there is opposite, because here, if I have a map here, the compositions act like that, and same reverse direction for x2. Okay, so this is it actually works well by just substitutions. The composition of n functors works well. So suppose okay, so suppose I have a map. Oh, okay. Cool. Yeah, so any map from y, any map here and here yields just a map that takes f to the composite upward and backward. Okay. Okay. So when we can look at the definition that it provides that for n equals 0, and so an element of cat 0 just corresponds to a poset with a naturality of the structural map that correspond to transitivity. So a poset with this definition is the data of objects and a truth value of between each pair of objects that gives a condition to be linked. Okay. Maps between posets inherit a poset structure. This is and just an application of the definition of n functors to n equals 0. And explicitly, two maps will be a map will be less than a map of poset is precisely the order preserving maps. And we can say two maps are the order on the map is given by the pointwise order because of this n formula. So and in the case okay, so we can define set in it's like so the natural numbers are defined in a very natural way by just stating 0 is of type n, and if x is of type n, then x plus 1 is of type n. And we also need to define the relations on the objects of n to achieve the proof of n is a poset, because I define it as a poset. And for this purpose, we just introduce, we define a relation by stating that x is less than x plus 1. So natural numbers form a poset. A set is a poset with additional structure, and it's important to note that posets are not sets with additional structure, but sets are posets with additional structure, because it may change some stuff when considering some other things. Okay, and so this is we define a set as a poset that is equivalent to its opposite, and that which means that we can reverse the truth value of okay, I think this is clear. So we write x is equal to y to y if the truth value associated is true. So a map between set now is precisely given by a mapping to any element of x associates an element of y, and such that it respects the equality. And this condition is important, notably when we consider quotient set. So I will talk about it in a minute. So the set of maps inherits an equality, which precisely gives extensionality because the equality of maps is defined as the pointwise equality, because the end in the case of sets gives a condition that should be satisfied for all x in X. We have also the poset of subset of a set, and the canonical embedding, just as usual. And we actually obtain a category of set that satisfies all of the axioms of lowers the elementary theory of the category of sets. The quotients are very easy to define. So if you have a relation on X, which just takes the form of a map like this, exactly like the structural map of X, it is required to satisfy some conditions well. And the objects of the quotients are defined as the same objects than X, and we just introduce a different equality, which is given by the relation. So
yeah, how many more slides?
Sorry?
How many more slides?
Yeah. Oh, okay. Maybe. Okay. Okay.
You might want to finish up, and then we'll have time for some
No.
questions.
Yeah. Okay. I'm sorry. Maybe I can stop. It's just Okay. Okay. You just have a notion of equivalence that gives equivalencies of categories, etc. And yeah, I wanted to talk about choice as well because
Sophia, it might be an idea to just go through all the slides so that somebody who's watching a video can slow down and watch it themselves.
yeah. Okay. Okay. Maybe. Yeah. Maybe I just observe. I just pass the slides so that okay. And um. Okay. Sorry, I've been a bit long.
Yeah, maybe key features
Yeah,
you'll
yeah. Go
show.
back to key features and right. Just
Yeah,
talk about
thanks.
this. Sum up using this.
Yeah. Yeah, I wanted to say that this framework is actually very easy to work with. It's very compact and everything works by induction. Literal expressions are processes directly into truth values, and uh, well, most importantly, it avoids the final process of interpretations of the judgments of as Boolean truth values, and well, it enables more general logics. And it also provides, we can work formally within this framework and don't consider the hierarchy of categories, but something else, which was my initial motivation because I wanted to work with sequences of categories. So, yeah, it is very, very general. And it encapsulates the nested nature of structures well. So it's strongly suited for higher structures. So everything is built actually from small pieces of um, of proofs, and the higher morphisms just decomposes to kind of a sequence of discrete stuff. So it's both computational and homotopical. Um, and well, okay. So there is a high level of freedom for generalization, like I said, because just change the the -1 level of truth value, and you obtained way more general notion of a set, etc. So yeah, I think it reflects the way we do mathematics because um, if I write X is an n category, well, I'm sure that what I'm writing is considered true. So I think that typing judgments should actually be truth values. Okay.
Okay, thank you. Uh,
Okay.
go to the last slide just so we can see what you.
Yeah, I wanted to. Yeah, okay. So I used this language in my thesis. So in the third chapter, if you're interested, well, I worked on a like two categories that are not cat, but that looks like cat. So in a formal way, and it can be seen as an expression of this language at level 2. Um, so you can also define operands within this framework, which is also in my thesis. And well, if you're interested by structure interchange, go look at the third chapter of my thesis.
Oh, may I just ask, what is structure interchange?
It's when you have different structures that are compatible with them other, you have an interchange relation that arises to express the compatibility between the structure.
In the
So would
sense
an example,
of
like let's say a ring that is also, a group if you forget the addition or something like that. I'm
Um,
sorry.
No,
if
I
it's
think she means about like horizontal and vertical compositions of natural
Oh,
transformations.
okay, something different. Never mind. Thank you.
They're homomorphisms of each other.
ah
Mhm.
you mean Goodman interchange law. That's
Right,
what you mean.
yeah.
right.
Well, the interchange law is an instance of interchange.
Hmm.
Thank you for
Any
talking the
questions?
question.
Thank you very much. Any
Yeah,
questions?
I have a short comment and question. A small historical point. I think when you say Aristotle invented logic and Euclid used in mathematics, I think historically just false, if you want truth. And I don't think it's just my opinion. It's actually what we find in Euclid, even he's younger than Aristotle. It's actually kind of mathematics that has been developed earlier, at least maybe about 2 centuries, certainly. And it's rather Aristotle who actually, we find a lot of example of the same mathematics as we see in Euclid's Elements, and it's rather Aristotle who kind of modeled his logic after mathematics. And by the way, it still didn't work smoothly, never. Say the syllogistic, of course, was not. There were many attempts to somehow put Euclid into syllogism. It never really worked. It's also important then you talked about rules and axioms in modern sense, right? In modern formal systems. And then of course it's different meaning of axiom, because axiom in Aristotle is rather a rule, like perfect syllogism is an axiom in Aristotle. So it's different actually notion of no, perhaps it's all not important. It just
Yeah, I
thought
just wanted to point at they use the notion of an axiom in the quite the same way. There is a the definition just corresponds to what we to some things that need not to be proved and which is irrelevant to be proved. But I didn't want to say that Euclid's work was based on Aristotle's work, but maybe thank you for making.
Yeah, but in another remark, maybe question, it's actually interesting this external internal. Now, one thing it's not always very clear. Probably you may try to formulate what really means. I think I kind of understand it, internal logic, like in topos and things like this, but there is, of course, geometrical analogy, at least, right? Like intrinsic geometry and some external. So one thing just probably define it better, but also I think I understand very much this, how say, philosophy of making everything internal. So I can kind of feel it. But historically, again, I think for people like Hilbert, actually this external point of view was really also principle, that not simply because they did want internal, that they couldn't do internal, right? They wanted to make it externally. And this is because the whole idea there, right, is that you may kind of make purely formal inference, forgetting. It actually comes from symbolic algebra. Hilbert explicitly uses this analogy, right? That you may calculate with symbols, forgetting absolutely all your meaning, right? And then come back to meaning. And that really gives advantage. And I think Hilbert wanted to use the same advantage in formal systems, of course, right? It's so he
Yeah,
did
but
not. Mm.
uh, I don't see any particular advantage to separate the semantic and the syntax at this point, because you can construct very weird things after that on a formal system, and this leads to
No, advantage is that you can kind of mechanically, as Hilbert would say, right? Say check something and compute, and then of course you would also put your semantics, but at certain point, kind of useful for forgetting. No, at least I don't think it's easier to how to say to get rid with this argument, right? Maybe you are right, but it's not immediately clear, and there is a lot of kind of mathematical practice behind it, and then coming at least from 17th century, maybe earlier, right? That we do certain things, or just think how we add numbers if they are sufficiently big, right? We don't really, how say, feel that it's not like we making like 2 times 2, but if it's kind of several digits, we do it mechanically. And that's kind of, how say, move in some situation, maybe not universally, probably still could be useful. But actually, just remark. But my really question is, actually, I wonder. So, do you think about this system as a kind of foundation or say language for all of mathematics, or also if so, do you keep in mind this idea of kind of how say formalizing in as a computer code, so we could use it for
Well,
like
yes.
talk or something, right? Uh,
Um, this is definitely a project to implement
mhm,
on a computer, and uh, something really convenient is that everything actually works by substitution. So I don't. Um, the point is that because everything is defined, each thing that is written has an attributed value which we can compute by substitution and substitution only. Um, so in this sense, I think actually I just wrote a LaTeX macro and I
okay.
can make computations with a macro just by
Mhm,
replacing the variable. So I think it might give interesting results and um,
but do you think this n category is really relevant in say every area of mathematics? I recently had exchange with Kevin Buzzard, and he started to be very much against homotopy type theory, all these n categories, because he says it's perhaps kind of interesting mathematics, but it's very special, and in usual mathematical proofs we simply don't need it. And so he speaks as a working mathematician, who I'm not. So I wonder what is your take on this.
Um, but well, you can stay at the level of categories, n equals one. Um, but I think it's often but it enables to the results are always more general and more encapsulated at the higher level. If you just look at it from higher, it will become considerably simpler in general because um, often the dependencies that lie between the objects are not captured by the first level, and you need to go a level higher, but I don't. I'm not. Yeah, I'm convinced of the the ability of n categories to describe efficiently structures, at least.
Thank you.
And yeah, I also think that analysis could be done by this way.
I think we're getting a little late. Any more quick questions? Anyway, Sophie, thank you for a fascinating talk. Um, it's very interesting. It's very interesting. Um, Anyways, thank you all. Next week, we're going to have Hannah's going to talk. And then in a few weeks, Andre is going to come and give us an in-person talk. So we're looking forward to that. And Sophie, you're always welcome to come back and show how you progressed and things like that.
Thank you very much. And
Okay.
Sure.
Okay, so we'll be in touch. All right, everyone. Have a wonderful afternoon. Take care.
Like
bye.
Bye. Elias, take care.
So